Hello and welcome to the Moxy tutorial series. This lesson is muscle VO2. This presentation is going to review the concept of VO2 at a systemic level from a respiratory and cardiac perspective. Then this concept will be applied on an individual muscle level so that we can learn to visualize the physiology through the SMO2 and THB data. VO2 at a systemic level is the total rate of oxygen consumption for the entire body. It can be thought of as an accounting of the oxygen consumed by looking at the difference between oxygen in and oxygen out. This is frequently measured from a respiratory perspective using a mask to measure the volume of oxygen content of inspired and expired gases. This equation shows the accounting method. The VE term is the ventilatory exchange in terms of the total volume of air that is moved through the lungs per minute. Sometimes the VE term is expanded into TV times RF, which is the tidal volume times the respiratory frequency. The tidal volume is the volume of air moved through the lungs per breath, and the respiratory frequency is the number of breaths per minute. The ventilatory exchange is multiplied by the difference between the fraction of oxygen in the inspired air and the fraction of oxygen in the expired gases. This gives the total rate of oxygen consumption for the entire body in terms of liters of oxygen per minute. VO2 can also be considered at the cardiac level. Measuring the parameters at this level is much less common than at the respiratory level because of the complexity of taking the measurements, but it's still a very useful concept to consider. Again, it's a matter of accounting of the difference between the oxygen in and oxygen out, but now it's with respect to the heart. The accounting equation closely parallels the respiratory equation. The first term is the cardiac output, which is the blood volume output of the heart. Just like the respiratory equation, the cardiac output can be broken down into stroke volume times heart rate. The stroke volume is the total of blood that is moved with each heartbeat, and the heart rate is the number of beats per minute. The cardiac output is multiplied by the difference in concentration in the arterial blood that leaves the heart and the venous blood that is returned to the heart. For some technical clarity, we are referring to the blood that leaves the left ventricle and the blood that is returned to the right atrium. The concept of accounting for oxygen in this way is called the Fick principle. This method of accounting for oxygen can be applied to muscle as well. Again, we're just looking at oxygen in minus oxygen out. We need to look at the flow of blood into and out of the muscle and look at the oxygen concentration in and out as well. This follows the same form of the equation that we've already been using. The blood flow is just the blood flow rate through the muscle of interest, and the oxygen concentrations are for the blood in and out of that individual muscle. We cannot use SMO2 and THB to directly calculate VO2 for an individual muscle. However, SMO2 is a very good indicator of the concentration of oxygen in the venous blood. THB is not a measure of blood flow, but as we've seen in earlier lessons, THB trends can give us indications about the states of blood flow just as when a venous or arterial occlusion is present. Generally, the VO2 concepts so far have referred to what's going on at steady conditions. When we are using muscle oxygen monitoring, we are frequently interested in what's going on during non-steady conditions. This requires us to consider some additional factors. The first factor is that blood flow into the muscle may be different than blood flow out of the muscle. The most obvious case of this is the venous occlusion. When the muscle tension restricts blood outflow, the muscle will start to pump up with blood. This is a non-steady condition because the muscle cannot pump up indefinitely. While the venous occlusion is occurring, we need to remember that blood inflow and outflow are different. The second factor is oxygen that is stored within the muscle. Oxygen is stored in the myoglobin and hemoglobin inside of the muscle. Depending on the available blood flow and the metabolic needs of the muscle, this oxygen may be consumed or replenished. This is also a non-steady consideration because there is a finite amount of oxygen stored. When it is gone, it can no longer be used for metabolism. It is easy to see the effect of this on the stored oxygen when a tourniquet is suddenly applied that completely stops blood flow. The SMO2 values drop over tens of seconds to minutes, while the stored oxygen is consumed by the muscle. This makes our accounting equation a bit more complicated to include these considerations. The total amount of oxygen used by the muscle is the blood flow rate in times the oxygen concentrations of the arterial blood minus the blood flow rate out times the oxygen concentration of the venous blood plus the oxygen used from what's stored inside of the muscle. Again, THB gives us some insight into blood flow in and out. The SMO2 value gives us insight into venous oxygen concentrations. And now we can add that the rate of change of SMO2 can give us insight as to when oxygen is being consumed from storage. A falling SMO2 indicates that the stored oxygen is being depleted. Next, we will apply this to some examples that can highlight how this can be used. This graph shows SMO2, THB, and heart rate during a steady load on a cyclist. During the time period of about 30 minutes to an hour, the SMO2, THB, and heart rate were all very consistent, indicating that the athlete was nicely in a state of homeostasis producing this load. Just a short deviation from the main point of the slide. It's very interesting to note that after about 1 hour, the heart rate starts to slowly increase even though the load, SMO2, and THB remained constant. Sometimes this is called heart rate drift. When we think about what's going on in this muscle, there are only a few possibilities for the source of this change, and here are 3 to think about. It's possible that some other part of the body started requiring more blood flow, so the body had to increase cardiac output to keep the muscle in homeostasis. It's also possible that the leg muscle started to use more oxygen even though the load was constant, and the body had to increase cardiac output to keep the muscle in homeostasis. It's also possible that cardiac output actually remained constant when the heart rate increased due to a simultaneous decrease in stroke volume. Okay, back to the main point of looking at homeostasis from that 30-minute to 1 hour window. During these conditions, the non-steady considerations that we talked about on the last slide are not relevant. The THB is constant, so we can assume that blood flow in equals blood flow out. The SMO2 is constant, so we can assume that no net oxygen is being used from storage or that storage is being replenished. This makes the VO2 equation reduced to its more simple form. An arterial occlusion can be thought of as applying a tourniquet, although it can also occur naturally from strong muscle tension. An arterial occlusion means that all blood flow stops. Let's take a look at how this fits into the muscle VO2 equation. Blood inflow goes to 0. Blood outflow goes to 0. The only thing that's left is that any oxygen used has to come from storage. In previous lessons, we've looked at how a venous occlusion shows up as a steady increase in THB. This is caused by muscle tension restricting blood outflow. This can also be considered in terms of the muscle VO2 equation. In this case, the blood outflow goes to 0 or at least becomes smaller than the blood inflow. So the equation reduces to the inflow and the storage term. It's possible for SMO2 to remain relatively steady for a short period of time during a venous occlusion because of the blood inflow. We have already seen that when a load is suddenly applied to a muscle, the SMO2 will drop rapidly. The muscle VO2 equation shows how this occurs. As soon as the load is applied, the muscle starts using oxygen immediately. However, the blood flow has not yet had time to react, so the blood flow numbers are small. This means that most of the oxygen being used is coming from stored oxygen. The rapid use of stored oxygen shows up as a rapid decline in the SMO2 value. The SMO2 stops declining when the blood flow has had time to adjust to the needs of the muscle. The reverse is true when load is suddenly stopped. Immediately after the load has stopped, the muscle VO2 becomes very small. However, the blood flow remains elevated for tens of seconds after the load has stopped, so most of the excess blood flow and oxygen extraction is directed to replenishing the stored oxygen. This is how the recovery occurs. This lesson brings home many of the concepts that were presented in earlier lessons. When coaches can learn to think in terms of muscle VO2, and when they can learn to use the insights from the values and trends from SMO2 and THB, they can learn to see the data directly in terms of their athlete's physiology. Thank you for taking time to view this tutorial.